Okay, in this example, we are asked to find the magnetic field between two cylinders when the space between the cylinders is filled with a magnetic material with magnetic susceptibility chi sub m. We are asked to do that in two different ways. We are asked to do it finding the magnetic field H first and using this expression. And then after we do that, we are asked to find the bound currents and directly find the magnetic field from the total current, including the bound and the free currents. So let's do the first problem first, which is let's find the magnetic field by first finding the H field. To do that, we are going to use Ampere's law. Ampere's law, we're going to look at a path here. We're going to make the surface like that, and the expression of Ampere's law in this case, right, is that this is the integral dl dot the H field must equal the total free current enclosed. Luckily for us, the free current enclosed is simply given by I, and again, using the symmetry, we're going to be able to say that the H field is going to have to be only in the phi hat direction. So if we make this the positive z direction, if we make this the positive z direction, then phi hat is going to be going into the page this way. This will be phi hat, and it will be coming out of the page this way on the bottom. Okay. And so we're going to say that H only points in the phi hat direction, and it only depends on the distance s from the surface. That's just a statement of symmetry of the problem. Coming back here, applying that to this expression, if I integrate around this whole thing, it's independent of phi, and so it's just going to be the circumference of that loop, and so that's going to give me 2 pi times s times h phi of s is going to be equal to, now I'm going to be a little bit more careful, this is I, as long as s is between a and b, and it's 0 otherwise, which of course very simply gives us what the magnetic field is. The magnetic field, or the magnetic field H, is then equal to I over 2 pi s, as long as a is less than s is less than b, is equal to 0 otherwise. Now we are going to use the expression, right, that the magnetization is equal to the chi m times this H field. So this is going to give us that the magnetization is of course chi m times I over 2 pi s, for a is less than s is less than b, and 0 otherwise. And finally, we're going to use the expression that the magnetic field B is mu naught H plus M. And so just adding these together with a mu naught, we get that the magnetic field P is going to be equal to mu naught I 1 plus chi m divided by 2 pi s between the cylinders, 0 otherwise. And so that's part A. For part B, we have to find the bound currents. To find the bound currents, we need to know the magnetization. Luckily for us, we've already found those. So we can just start that out. And so I'm going to start out asking what is the bound current, the bound volume current. The bound volume current is del cross M. In polar coordinates, and so look this up in the front of your book, the terms we have to worry about on the curl of M is minus partial with respect to z of the phi component, on all of these up here, I missed that. This is, of course, in the phi hat direction, and the phi hat direction. I missed that in all of these, sorry. The phi hat component of m, which is chi mi over 2 pi s, the s hat, plus 1 over s, partial with respect to s times the phi hat component of m, which is chi mi over 2 pi s, in the z hat direction. So those are the non-zero parts that we have to worry about for the curl. First, this is independent of z, so that is 0. Second, these s's are going to cancel, and then this is independent of s, and so that's going to give 0. And so this is the bound current density, JB, and we see that the bound current density is going to be 0 everywhere in the bulk. Okay. Now we have to worry about the surface terms, KB. This is simply m cross n hat. For us, we have two surfaces. We have to actually worry about the surface on the interior. In the interior, our n hat, okay, on the interior, n hat is equal to minus s hat, and then on the exterior, this one here, right, n hat is equal to positive s hat. Exterior n hat is equal to positive s hat. So simply plugging that in, I'm going to get that KB, and this is evaluated at radius A. Okay, so this is on the interior. This is chi mi over 2 pi a, and then I have phi hat cross minus s hat. And so if I use the right-hand rule, phi hat cross minus s hat is positive z hat. So this is in the positive z hat direction. And so this says that the surface charge on the interior is chi mi over 2 pi a z hat. On the exterior, the bound surface charge, chi mi evaluated at the exterior, so it's 2 pi b, phi cross s hat, which of course says that chi minus chi m I over 2 pi b z hat. Now, all we need to do is do the same math we did up above. And so up above, we did some math to find what the total, or what the magnetic field H was. We do the same thing to find B. Here, the curl of 1 over mu naught B is equal to the free current, JF. That, of course, translates to the path integral dl dot 1 over mu naught B is equal to not f, jf plus jb, is going to be equal to the total current enclosed, right? So total enclosed. Now we have to figure out what the total enclosed is. We're going to use the same trick again. We're going to say that B is only going to exist in the phi hat direction because of symmetry. It will only depend on S. And we have to figure out what the total enclosed is. Well, the total enclosed is going to be I, and then plus, now we have the surface current, but we have to multiply it over a length. What is the length? Well, the length is actually this full circumference that we have here. So this is going to be the surface current on the interior, chi m I over 2 pi a, but the circumference is, of course, 2 pi a, which perfectly cancels out. Go figure. And so this is going to give, I1 plus m. Now, on the exterior, right, I total, if we've gone to, so this is for a less than s less than b. It's of course 0 for s less than a, and this is for s greater than b. We're going to have 0 because we have the plus I going in and the minus I going out. We're going to have this chi mi term, that's the positive going out, and we're going to have minus the chi m over 2 pi b times the circumference on the exterior. But the circumference on the exterior, of course, is simply 2 pi b. And so that is also going to give 0. And so here we're going to run across the final solution that the magnetic field everywhere is going to be equal, so now whenever we do this expression, B is independent of phi, it only depends on s, and so we're just going to get 2 pi s, that's the circumference, that's its integral dl, 1 over mu naught b phi of s is going to be equal to, now we have this I1 plus chi, or 0, and this is for a less than s less than b. Simply solving, moving things to the other side, we get that the magnetic field in this case is going to be mu naught I 1 plus chi m divided by 2 pi s for a less than s less than b, and 0 otherwise. Which of course is exactly what we found up here using the H field instead of the B field, or instead of the full bound and free currents. So you can do it either way, and you should get the same answer both ways.